Okay. I'm gonna go through back real quick again at the beginning. Um, so the people that could make it can watch this. I'll upload it to YouTube. But and then I got by the way, I had like half an hour and I got another meeting. But anyway, we're just going through on just like how to play around with data in R for the purposes of what we're doing with the LA Waterkeeper. Um, just real quick, this opening line here, this just means remove all remove all variables in the environment. So basically purge memory. I mean, you don't have to, I just usually do as a habit. All of these are packages that eventually I end up using to do all the analysis here. Um, these are all for doing things like tidyverse, dplyr, plier. These are all ones that deal with data manipulation. Dismo and Dismo's to do, and random forest are to do things with modeling. Desk tools is like a statistic one. And then ggplot, Viridis, and cowplot are all like basically dealing with visualizing data. All right. So you can just run stuff. Actually, a real quick way to run a bunch of lines at once. You just highlight them and hit click run. Ooh, look at that. All right. And then set the working directory. This is wherever you want. This is actually wherever your data is going to live. This is where your script's going to live. So you run that. And then the link, this is where, so the GitHub is actually where all the data we're using is available. And now we're going to read in the CSCI data, so the California Streams Condition Index data, into a data frame. And just to go over this again, the header equals true, forces it to recognize that the top row in your file is the header, which is the variable names in the data frame. The separator means, okay, it's a comma separated value in this case. As is true, basically force it to read through everything, even if it's blank, and just turn a blank value into an NA. Skip equals 0 means don't skip any of the lines. Fill equals true is another one to like force it to fill in blank values just as NA. Quote, this quote thing is to like force it to recognize spaces as just like another character, so it doesn't like try to break columns at spaces for like, let's say, variable names, which is really annoying.
Hey, Levi.
Yeah.
Carissa was wondering if you could send her a link to the Zoom.
Oh, yeah. I thought, okay, hold on real quick. Let me, yeah, it's in the, email. I'll just email it to her really quick.
Yeah, I just told her it was the same link as the normal weekly meeting.
Yeah.
I think it was. So she'll probably just hop on in a sec.
Okay,
she probably has it.
All right. Yeah, again, I apologize that like I had some weird sound issue that was taking forever to fix. Okay. Oh, all right. Back to our studio. Okay, so anyway, we're going to read this in, and now we can look at it in the environment and just see like, okay, all the data got read in, and each column header is now a variable in that data frame, and you can extract one variable at a time by doing things like the data frame name. Okay. To do the data frame name, and you do $, and then whatever you want to look at. So, which is the variable name, and it'll extract all of them. And by the way, you can do multiple columns. There's all sorts of like things you can get into with doing data manipulation, but just like at least just doing one column at a time. That's how we do it. All right. So now the next step is we want to start creating a standard date format for everything, so that when we're dealing with multiple files, all the dates are going to have the same structure, so that when we combine things, the computer knows to link everything together. And the reason we're going through that is just that we're creating a unique sample ID based on the location, the date, and which experimental replicate it was. So there's anywhere between 1 to 3 replicates at each sample. But this is just to like separate out samples so they're all uniquely identified. All right. So the first thing is just to treat sample date, which in this right now, is a character string. And the way we can check that really quick is just the command str gives you the structure, parentheses. By the way, like if you type part of the way and you don't want to feel like typing the rest of it, you just hit tab, which is really great. And then in this case, okay, sample date. So if we just do structure in this column, it'll tell us the data type, which in this case is a character. Now, we want to convert this to a date format. So we convert it, the data type now is as date. So we're going to run this, and you'll see what happens here. So now we'll run that command. And by the way, here's another thing in RStudio, which you may already know. If you don't feel like retyping the whole command, you can go to the previous things you type by just pressing the up arrow. So now we're going to rerun structure, see what happens. And now it's listed here as a date, which is actually a different type of data format. Okay, so now that it's formatted as a date, now we can actually just quickly manipulate the whole process here. So when we sample date, that's the original format was year, month, day. And what we want to do is convert it to month, day, year, because everything is, a lot of the files, it's Squirp. I think that's the most common format, so that's kind of the one I ended up going with. So everything we're coercing, we're formatting and say, okay, take that date and then reformat it. So if you see here, right, we have the structure that's year, month, and day. So I'll show you what happens when we reformat it. Okay, so now when we like extract and look at what it looks like again. Yep, so there you go. Uh-oh, what is this? Hold on a second. Okay. All right, cool. So now when we rerun it, now you see now it's in the format of month, day, year. And by the way, replace the slashes with, the dashes with slashes. All right. By the way, if this seems mind-numbingly like tedious and like detail-oriented, it's like, I'm sorry, this is the way computers are. But I'm walking you through this so that when I start showing you some of this code, I'm when you kind of understand like what's going on here. And you'll get more of a head start on like being able to deal with, okay, here's the tedious stuff. Now what's more of the interesting stuff we can do? Okay. So I've reformatted this. Now I want to create a unique sample identifier. And this is, again, just like I want to uniquely, like basically it's a barcode. In this case, what I'm doing is going to combine by station code, which is just like the location, the date, and then the last one's the field replicate, which is just sometimes more than one sample was collected at time and place, but we want to uniquely identify them just in case like there was some wildly different results. So now we're going to create a new column, and you can create a new column literally just by naming it. And I'll just keep in mind when you're looking at this, you see like this is the number of rows, this is the number of columns. When I create a new column, it should bump up to 49 variables. And now when I run it, there we go. Let's see what that new variable looks like. All right. And then by default, R always puts the newest variable to the far right. Okay, here we go. Here's unique ID. So station code, date, field replicate. So now every sample should have its own unique identifier. This is going to be really useful for actually like pulling all this stuff apart and looking at one sample at a time. Okay. Now, remember what I said, like there's tons of data here. So there's 49 variables we have here. Most of those are not going to be useful for what we want to do. It's useful for lots of other things, but for the purposes of what we're trying to do, we only really need to know, okay, what's the sample ID? I'm also just separately including the station code. And this thing here called the SMC shed, this is an identifier for the watersheds. So things like Los Angeles, San Gabriel, Ventura. And then HUC is hydrological unit code, which is a numerical code corresponding to those watersheds. So I'll show you what that looks like in a second. And then the year, and then the CSCI score. So the CSCI score, by the way, is just the actual data we want for just biological integrity. So now I'm going to create a new data frame. And by the way, this is what I said, like we can select more than one column at a time. If you do a data frame and then you bracket here, comma, anything after that comma now is going to be just the columns. So the first, anything to the left of that comma is going to be selecting on rows. So we only want we want to select things by columns. So we're doing everything after the first comma, and then it's C. C is just a way of saying like, okay, concatenate or like turn things into a list. So now it's saying like, all right, give me all the columns that are in this list of names. So in this case, it's unique ID, station code, SMC shed, and so on. And it's going to extract just those 6 columns. So when I run that, now I've got a new data frame that's 6 columns wide. And here's what they look like. So unique ID, the watershed name, the HUC or hydrological unit code. By the way, there's like codes for like literally every watershed in the US. And so this is the data we're playing with just for the CSCI. Everything else we don't need. It's just useful for other things, for other researchers, not for us. Okay. So that's gotten us to like, okay, here's what our CSCI data looks like. By the way, stop me whenever you have any questions. Okay. And the next data we're interested in looking at is the chemical composition data. In this case, it's just the chem CSV, reading in it using the same long stretch of like qualifiers. By the way, if you want to, like I can, like I said, I can share this code. So like, I'm not asking you to memorize like all the qualifiers in this. This is just like things you just kind of learn over the years. But now we're going to create a new data frame that's just reading in all the chemical data. All right. Oh my God, look at all that. Now there's way more rows here. And here's why. Okay. The reason why there's way more rows. So if you see here, it's all okay, station code, sample date, and all this other stuff. It looks like there's a lot of things that look the same from row to row to row. Here's why. This is the key thing, is the analyte name here, is that there's all these rows, there's multiple rows per each sample because multiple chemical analytes were taken for each sample. So in this case, like we're looking at aluminum, ammonia, arsenic, chloride, all this. So these are all different variables for each row. So this is why this data frame has like 63,000 rows, whereas the CSCI has only got about 1,050. So again, there's a lot of other data types in here. So we'll play around with all that. Anyway, so, okay. Anyway, so this is all the information here for the chemical input. Again, we want to reformat the data type, the date frame, like the date structure, so it's the same as the CSCI. So we're just going to run through that process again. We're going to do the same process of creating a unique identifier. And again, we're creating a unique identifier because now both the data in the chemical data frame and the CSCI data frame will have something unique that will allow us to join the two. So we can both identify, we can identify samples, the same sample, both on chemical data and biological data, because they'll have like the same identifier. So we're going to create a unique ID. And just like the CSCI, we're going to only subset, we're only going to keep the information we're really interested in, which is the sample ID, the chemical analytes that were taken at that sample, so that varies. And the last variable here is called result, which is just like the numerical value representing its concentration. So like, micrograms, milligrams per liter, that sort of thing. Okay. So now we have this data frame here. So this is chem. This is, okay, unique ID. So the sample ID, this is like all the different types of chemical analytes taken at that sample. Here are the numerical values for this. And what I wanted to do, now there's different ways we could probably think about this, but I was going to step through this whole process here, which is I wanted to just get a list of all the chemical names. And the reason being is we don't always take the same chemical data every time for every sample. Sometimes only 20 of these analytes are taken at a sample. Sometimes it's 300. And overall, there's 671 unique chemical identifiers. So I wanted to just get an idea of what all the unique chemical information was there. And I created sort of this list. And by the way, this is what the unique command does, is it takes a list of, it basically can take like a column, like a vector in this case, and says, all right, give me all the unique values. So it removes all the duplicates. So we run that. This is what we get. We get a list that's 671 characters. It's 671 unique strings here. Every single thing. All right. And what we wanted to do, this gives us like, this will give us something to play with. So in terms of figuring out like, basically trying to standardize the chemical data we have, because remember, like if sometimes we take 20, sometimes we have 300 unique measurements, we want to at least compare it against sort of the overall like master list, which in this case is 671, so that when we compare sample to sample to sample, we have a unique comparison tool. All right. Now, what I want to do is I want to go back here, and then there's some stuff I was going to play with. This convert off-scale values to NA. I want to show you why I'm doing this. And this is just, again, this comes with like playing around with this data for a long time. But in the data frame, if you want to sort stuff, you can just click on the arrows here. All right. So now I'm like looking at lowest to highest. So if you see here, we have all these values that are like negative something. This is not because there was negative 99 milligrams per liter of cadmium. This is because this is like a numerical way when they're doing field work of saying like, this was off scale, or there wasn't like, we weren't measuring anything. It's sort of annoying, but it's like sometimes if you use like a multimeter, an electric multimeter, it'll show -1 on stuff. Anyway, but the negative stuff, this is not data. So what we want to do is we want to convert all of these negative values to just, we were just going to convert these all to just like to NA, not 0, because 0 would mean like we actually know it was 0. NA just means like I don't know what it is with any reliable measurement. It probably was just some like they just never took the data. And so to get rid of those values, you can just quickly go like, okay, data frame bracket, and then say convert all the data frame values, in this case our chem data frame, that are less than 0, convert them all to NA. So when we run that, what do we get? Oh, okay, well, it flipped it around again. So now, and if I want to look at the range of values, I just like mouse over here, and it says numeric. Wait, I thought I got rid of the negative values. Oh my God. Okay, there we go. So now it's all real values. So we have like 0. And if I scroll down a bit, it should be a little higher. Oh, okay. Oh, there we go. Okay, so now like it's really small concentrations. And if I scroll all the way down here, okay, so larger values. But now you see, oh, all this NA. These were values that were like -99 or like -88 or whatever. And we just said like, all right, we know that's junk, just convert it to NA, which just means no, like not applicable, no observations. All right, cool. Now this next thing here is horrendous. Let me kind of walk through this whole line of code here. Let me see if there we go. So this entire process here, and this is not something I would expect you to like figure out quickly, but I'm using a package called, this is dplyr. And dplyr's got all these data manipulation tools. And I'm going to step through what it is doing here. What I want to do is I want to reformat this and by saying like, okay, group take the chem data I have, make sure that it's all grouped by unique ID, so all sample ID, and make it so that, all right, I have, and this dplyr mutate passes to something called tidyr spread. What this is doing is it's saying, remember those 671 unique analyte names? It's saying, okay, what I want you to do is take the unique ID, remember how we had multiple rows for every unique ID? I said, all right, let's change take our data and reformat it such that we only have one unique row for each unique ID, so for each sample ID, and now we have a unique column associated with that row for each analyte. So now instead of having 20 rows or 300 rows or 45 rows corresponding to chemical measurements for each sample, now we have one row for each sample, and we have the same number of columns, in this case 671 for each sample, for each chemical analyte. Now you're probably wondering well, but if you're only taking 20 measurements, if you only have 20 chemical analytes and you have 671 columns, what does that mean? It's well, it means that most of your columns are just going to be empty, but it means that everything's going to have a unique format. I mean, you'll have a uniform format. So that's what this entire long chunk of code is doing here, is it's saying, okay, force it so that we're going to change the entire structure of that data frame so that it's a unique row for every sample and then columns for each chemical analyte. So it's going to standardize our data format. So now when I run this, and it'll take a sec, so it's got to think because it's doing a bunch of math right now. Thinking. So now we have 672 variables. We have all these observations here. And what we're doing is if I go here and I go to, well, if I open this, it's going to take a while. Let me see if I can, okay, I can open this, but it'll take a little while to load. So as it's loading, okay. So now you see we have unique ID, and now we have a column for each chemical analyte. And it's giving me the pinwheel because it's thinking real hard. Okay. And you can see a lot of this is just NA because a lot of times we're not measuring a synaphthene. I can't even pronounce that one. All right. Let me scroll ahead to one I can pronounce. Okay, acid neutralizing capacity. Great. So all this stuff, a lot of times we're not measuring this, but we scroll through here. See, okay, sometimes it's really common. We usually measure ammonia. Ammonia is N total, that sort of stuff. These measurements happen a lot. So we're going to do, so we have all this measured, but most of the time, for most samples, we're not measuring it. Great. So now we have all this, but we still have a problem. I'm going to scroll back here. We have row. All this, it's the same damn sample ID over and over again. I made a unique column for each variable, for each analyte, but now I have a lot of redundancy here. So this row just repeats over and over again. So what I want to do is I'm going to collapse this down so it's literally one row per sample ID. Okay, to first do that, what I need to do is I need to make all the columns numeric except for the first column. So what I'm doing is here, take chem, that's a 2 colon to number, n col, which means number of columns. So in this case, 672. So take columns 2 to 672 of that data frame, which basically means everything except the first column, which is your unique ID, and convert them to a numeric value. We need to make these numeric to do the next operation. Anyway, to do this and to do all of them in one shot, sapply means say okay, apply this conversion to literally every column. So we're going to take every column except for the unique ID, make them numeric. And that's what this is going to do. Now so if I actually first, if I just show you what the structure looks like, if I do str chem right now, yeah, so it's going to give you all these different, it gives you the data types here. And you notice it's all int, it's integer. So we can't, if it's integer, it's whole numbers, and it's going to cause problems when we do math down the line. So we have to convert it to numeric, which is a floating point, so decimals. So now when I run this command and convert it, and it's thinking because it's got to do this for 671 columns. All right, there we go. Now when I look at the structure again, okay, now it's going to, okay, now it's, again, it's integer, but I guess it's kind of hard to see. Some of these data types, yeah, it scrolled through all of them. Okay, so it's all, Okay, here we go. Yeah, it still says integer, mostly just because it doesn't print out all the columns. Anyway, okay, I guess that wasn't a very clear thing to show you, but like some of the columns further up that it doesn't print all the way out were not integer to begin, were not numeric. So anyway, this standardizes it so they're all numeric. So sapply, by the way, or lapply, or there's like a different apply functions in R, basically allow you to do like multiple operations all in one shot. It says just do it for everything. Okay. Now that everything's numeric, except for that unique ID, what we can do is now we can take this data frame, and this is again using a function and deployer called summarize, and it's summarize if, and it's saying if your columns are numeric, which is every column except the first one, take their sum, and if there are any missing values, just ignore them. So na.rm equals true, it just means ignore it in the operation. Like, so don't try to like add missing data. And when we do that, what it does, it's going to collapse all those rows so that now it's just one unique row per sample ID. So now if we do that, check this out, look at chem. So it goes from 63,000 or so observations to 1,219. So now when we open it up, this is what it looks like. Okay, it's going to think. This is a really big data frame. Think. Come on. All right. So now we go back. Now we see, okay, now we have a unique sample ID for each row. And now all that stuff numerically, it just collapsed. And now, like a lot of times, like it was missing data or it was just zero. So now it's just collapsed. And now we just have all this information here, all summarized one row at a time. And it's really sparse, except for, okay, so there's a lot of things, like things that get measured really often are like ammonia, different types of ammonia. But yeah, a lot of these things don't get measured very often. But we're including all of it in the model because some of them might have been, we don't know yet. Anyway, you can get the idea. Like it's a lot of chemical measurements. Okay, so now we have a chemical data frame. Now we have our biological data frame. So the chem data, the CSCI data. Now what we want to do is we want to merge them into one unique combined data frame. And that's why we did that whole thing with making a unique ID. It's because now when we use a command called merge, the computer knows where to combine the data frames on. So if both basically picture of two spreadsheets, they both have the same unique IDs for samples in each of them. And now when you say merge, the computer knows, oh, combine them on that column. So now basically picture like you're gluing two spreadsheets together where they match, and now the computer knows where they're supposed to match. So when we do this and we run and make the merged one, we get streams, which now has all the chemical variables, so 677, and all the biological variables, and there's one less because they share that unique ID in common. So that's still in there. Now you're probably wondering like, wait, how come there's only 687 rows here when I have over 1,000 on both of these? And the reason is because there are sites where we have biological data, but not chemical data. And there are sites where we have chemical data, but not biological data. So this streams is where we have both, because that's where we can actually have enough data to build our model with. So these are, we have 687 samples where we have both biological and chemical data. All right. So it's probably a good point to like sort of like wrap up for this time, but this is just getting the data in the format of just getting your combined biological and chemical data. Again, I can share the code, but I wanted to walk through like what's going on here. And then like I'm going to stop in a second, but all right, any questions you might have at this point? No? Oh no. Hello?
Hello.
Oh, okay. I just want to, all right. Sorry,
Sorry,
I'm just really paranoid because like my sound would not work like an hour ago. So that's why I'm like,
No. I was able to hear everything.
Oh, okay, good.
Yeah. Are we okay? So did you say that you were going to be sending out your your code?
Yeah, I can send out, what I can do is I'll send out what we went over. I don't want to send out all of it yet. But I'll send out just this chunk for right now if you want. And I can send everybody the link.
Okay, sounds good.
Okay. All right. So yeah, but I just want to get started with this. Oh, all right. Hold on one second. I have somebody from my next meeting is now starting. Okay, so what I'm going to do, I'll stop record here and wait, hold on. All right, there we go. 1 6. Stop.